So which was halogens and their trends in volatility and their colors, etc. So what we studied in that was that all halogens are diatomic molecules and Cl2, Br2, I2, etc. And they have the non-polar. So they just have temporary dipole induced dipoles, electrons randomly fluctuating. Sometimes this side is negative, this side is positive. Sometimes this side is positive and that side is negative. So the molecules during random collisions, they have temporary dipoles, induced dipoles. And down the group, you have more electrons. So you have more van der Waals forces, more TDID. So which is why the melting points and the boiling points, they increase when you move down the group. Here, that's one thing. And then you have, so you need to remember the states of these compounds. Okay, fluorine is a gas, chlorine is also a gas, bromine is a liquid, and iodine is a blue-black solid, which is yellow-brown in aqueous solution. And then we talk about the bond strength. Remember, the rule is that smaller atoms have stronger bonds. I mean, this is the rule. Usually smaller atoms, most of the time they have smaller bonds because they're closer to each other. Smaller atoms, so the reason why smaller atoms have stronger bonds is the atoms are less shielded. Atoms and the nuclei are less shielded. There is more orbital overlap. So there is more orbital overlap and there's smaller bond length. I just explain everything. Okay. Smaller bond length. So what that basically means is that that if you have an iodine atom, or let's say a bromine atom, a bromine atom has a lot of electrons. So bromine has 35 electrons, which is 2 in the first shell and 8 in the second shell. It's got 7 in the last shell, and I think it's got how many? It's 15, 17. So it's, I think, 18 electrons in the. So it's got 18 in the third shell, which is basically like if you write the electronic configuration, it's 1s2, 2s2, 2p6, 3s2, and then you have 3p6, and followed by 4s2, and 3d becomes 10, and then 4p5. So it's got 7 electrons in the last shell. It's got 18 electrons in the third shell, 8 in the second one, and 2 in the first shell. So that is bromine. So if I draw a bromine atom, the bromine atom is going to have 4 shells. So 1, 2, 3, and that's your 4th shell. Let me just. So that's 1, 2, 3, and 4. So that is what a bromine atom would look like, and I need 2 of them. So here's the second one. Here's my second bromine atom. And lots of electrons, 35 electrons. So it's 2, 8, and 18. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And it's got 7 electrons in the last shell. Let's go. So the only thing I'm trying to explain here is that bromines are going to form, this is the outer shell. So both bromines would form a covalent bond and they will form a diatomic molecule. But the thing is that the nuclei, the positive nucleus are so shielded that they're not really interested in each other's electrons. They can't even handle their own electrons. So both bromines would try and pull each other's electrons, and eventually they would start to share electrons between them. So the two electrons in the middle are going to, those are going to be, they're going to end up forming a covalent bond. So the two electrons in the middle over here, and they're forming a covalent bond. The only thing is that the nuclei are too shielded. This nucleus is not really interested in this electron because it's too far away, which is basically bond length. That the electrons, so remember there's a bigger bond length. The bond length is really, the electrons are really far away from the nucleus. So this nucleus and this nucleus, they're not really that attracted to these shared electrons. So that is bond length. That is what is meant by bond length. So there's going to be less orbital overlap. They're not going to pull each other's electrons. So the electrons overlapping with each other, that's not really going to happen that strongly. So there's going to be less orbital overlap. So smaller atoms always make stronger bonds compared to these bigger atoms, because bigger atoms are really, really far away. Okay, so remember this rule. Ye clear? Anna, is this clear? Hania, Alicia, is this clear?
Yes,
Sir, could you please explain it again, please?
I'm going to one second. So remember this one is the O-levels diagram, right? Hani, remember what is a bond? It's a bond is basically electrons being. I'm gonna go over a sigma bond. For example, a hydrogen atom. A hydrogen has one electron in a spherical region. There's a negative charge. That negative charge is spread around in a spherical region over here, right? That's one electron. And I've got another hydrogen atom, which is exactly the same, 1s1. It's got the negative charge of one electron is located in an s orbital over here. So there's this negative charge that's spread in this spherical region. How is a bond formed? This hydrogen nucleus sees the other atom's negative charge, it starts pulling on it. This hydrogen atom's nucleus sees that negative charge, it starts pulling on that. So what happens? Where is the negative charge now located? So you have the two nuclei, and they're trying to attract each other's electrons. Now what happens is that the negative charge is mostly now concentrated in the middle part over here. The two electrons are now most likely to be found somewhere stuck in the middle over here, and that's basically your sigma bond. So Hani, is this point clear so far?
Yes, sir.
Now, this is known as an orbital overlapping, with one orbital overlapping with the other orbital. That's a sigma bond when it's an end-to-end overlap of orbital. Both atoms are trying to pull each other's electrons. So the electrons are stuck in the middle. Now, imagine the same thing, that both atoms are trying to pull each other's electrons, but the nuclei, who's pulling the electron? It's the nucleus of the atoms, right? This nucleus over here is trying to pull the electron from the other atom, right? Now, in the case of bromine, if you have bigger atoms, what happens is that the nucleus is already surrounded by a lot of electrons. So why would this nucleus be attracted to the electron from the neighboring atom? It's not really going to be attracted to the electron in the neighboring atom. Just a second, let me. इसको उठा के वापस कर देते हैं.
Sir, did you say the nucleus is attracted to the electron of the other atom?
Yeah.
Okay, thank you.
Okay, that's, let me move this as well. So, Hani, the point is, this is the nucleus of the hydrogen atom, and it starts pulling on the electron of the neighboring atom, right? It's a negative charge. And eventually the electrons get stuck in the middle because both nucleus is trying to gain those electrons. Now, in the case of a bigger atom, what happens is that the nucleus is already very shielded. It's surrounded by a lot of electrons. So the point is, the attraction for the neighboring atoms' electrons would not be that strong. Anya, is this point clear?
Yes,
So the point is that there's going to be less orbital overlap because they're not going to pull each other's electrons that strongly. Right? Both atoms are trying to gain each other's electrons, but the orbital overlap is not going to be that strong. I mean, like the hydrogen atom, the orbital overlap is very strong, which means the two electrons are most likely to be found in the middle part, because they're both holding on to each other's electrons, trying to pull each other's electrons very, very strongly, but not in the case of bromine. In the case of bromine, the atoms are trying to pull each other's electrons, but not that strongly. That would be a very weak attraction because the nucleus is very, very shielded. So it's not going to be that interested in the neighboring atoms' electrons. So whenever you have a bigger atom, it's not really that interested in bonding in the first place. It's not going to be interested in any of the electrons from the neighboring atom because it already has too many electrons with it. Is this clear?
Yes.
Yes, sir.
So this is what is meant by why do smaller atoms have stronger bonds? Because the nuclei of small atoms are less shielded. So they would try to pull each other's electrons very, very strongly because there are no other interfering electrons, other orbitals even available. There's going to be more orbital overlap, and the length of the bond is going to be very small. They would be very close to each other. So they're going to attract the electrons even strongly. So that is why smaller atoms make stronger bonds. But then you've got an issue over here, which is right over here. Okay, why? Not this one. We were talking about this one. So you've got an issue over here. Bigger atoms have weaker bonds, but fluorine is an exception. So remember that fluorine is an exception, and the reason fluorine is an exception is so the fluorine-fluorine bond is very weak, even though it's a small atom. So what's the reason behind that? The reason behind that is, here's a fluorine atom and here's another fluorine atom. There's less shielding, obviously. They just have two shells. That's it. So this one has a total of 9 electrons, 2 and 7. This one also has a total of 9 electrons, 2 and 7. They both should, because they're very close to each other. So they both should preferably attract each other's electrons, right? Very, very strongly. They should attract each other's electrons. But the thing with fluorine specifically is, okay, fluorine has too many lone pairs. I mean, the nuclei are very, very strongly attracted to these shared electrons. I mean, they're close to it. The bond length is very small. It's a small atom, so they're very close to it. So they're very strongly attracted to the electrons. Saib, are you there?
Yes, sir.
अच्छा, वो कब है MCQ एग्जाम कब है, किस डेट को है?
I think it's at 16 or 18.
16th और 18th. ठीक है. अच्छा, तो ये वाला. Okay, the nuclear. So I mean, there should be strong attraction, but another thing happens in fluorine, and that other thing is that fluorine has a. Huh?
It's at 16.
ठीक है. I said now the other reason is that why is the bond weaker? That fluorine has a lot of spare electrons. Its outer shell is already complete. It's got a lot of lone pairs. So these electrons, they repel each other. So the fluorine atom, the two fluorine atoms cannot be kept very close to each other. that even though the nucleus of the two atoms and the shared electrons would be very strongly attracted, but because fluorine has so many lone pairs, it's got 3 lone pairs over here and 3 lone pairs over here. The electrons of this atom and the electrons of this atom, they start repelling each other very, very strongly, which kind of weakens the bond. So the lone pair repulsion between fluorine atoms it weakens the bond. Okay, is this clear?
Yes, sir. Yes.
I mean, that issue is not here because it's a bigger atom. The atoms are already very far away from each other. So, I mean, the repulsion would be here over here as well. But since they're already very far away, so that is not an issue. Okay, they're already very far away from each other. So there's not going to be, because of the distance, the repulsion would be lesser. But because the fluorine atom is so small that the lone pairs are now right next to each other. So which is why they really strongly repel each other. So it's very hard for the two fluorine atoms to be very close to each other, even though they're attracted to the shared electrons, but the repulsion would be very, very strong. This is the reason why the fluorine bond over here, its bond energy is very less because of the lone pair repulsion. So the exception is F2. Why? Because the lone pair repulsion weakens the bond. Is this point clear? Just a second.
Yes, sir. Yes, sir.
Hania, is this clear?
Yes.
So now, when it comes to the HF bond, the hydrogen halide bond, HF, HCl, HBr, HI, that's not an issue there. Why? Because the HI big atoms, they form weaker bonds. Small atom, they form stronger bonds. So why is HF forming such a strong bond over there? The reason for that is the lone pair repulsion is not an issue when it comes to HF, even though it's a really, really small atom and they're very close to each other. So it's not an issue in that particular case. And the reason for that is that H has no lone pairs. I mean, the H atom does not have any other electrons apart from the shared electrons. That's it. And the fluorine has lone pairs, but they don't have anything to repel. I mean, this fluorine atom and its lone pairs are not going to repel anything. So the only attraction that exists is the nucleus of the H atom and the nucleus of the fluorine atom. They're both attracted to the shared electrons, which are over here. So both of them are attracted to the shared electrons. So there is no lone pair repulsion. So no lone pair repulsion whatsoever. So यहाँ पे either issue था कि when you had two fluorine atoms, so this had lots of spare electrons. This also had a lot of spare electrons in its outer shell, and they started repelling each other, which kind of weakened the bond, which was over here. But you don't have that over here. This lone pair, the hydrogen atom has absolutely nothing to repel. ठीक है, is this also clear?
Yes.
इसमें याद रखना कि when it comes to bond strength, bigger atoms form weaker bonds. Fluorine was an exception because there were too many lone pairs, which is why the atoms were very hard to put the two atoms together, which is why fluorine had a very weak bond. And you had no exceptions when it came to HF, HCl, HBr, HI. Bigger atoms, they always form weaker bonds. Smaller atoms, they always form stronger bonds. Then we're going to discuss the boiling points of hydrogen halides. So the boiling points of hydrogen halides is that HF has hydrogen bonds So which is why HF, and let me do this over here. Copy. Achha, so let's discuss their boiling points. First one, remember, when it comes to HF, it has hydrogen bonds, and you might be asked to draw those hydrogen bonds. Now, hydrogen bonds were extremely polar molecules, where fluorine is one of the most electronegative elements. So what happens is you get a very highly polar molecule. You got a hydrogen which is partial positive, you got a fluorine which is partial or slight negative. And the bond polarity is really, really high. Why? Because fluorine is one of the most electronegative elements. 3 elements form hydrogen bonds. It's either fluorine with an H, or N with an H, or O with an H. That results in a very polar bond. And the reason why fluorine also has an even greater negative charge is because fluorine has lots of spare electrons, these lone pairs, in their outer shell. So the negative charge increases because of that. So if the negative charge is increasing, the HF molecules, 2 of them are going to attract each other very strongly. So you've got another HF molecule, and so you got another HF molecule, and that HF molecule has lone pairs as well. This is partial positive, this one is slight negative. And the 2 molecules are going to attract each other. The lone pair of 1H will be attracted to the positive H of the other molecule. So you got really strong hydrogen bonds. So what about the boiling points of HCl, HBr, and HI? So considerably lesser. First thing, there is no hydrogen bonding between these molecules. Can anyone tell me which one has the strongest permanent dipole between the 3? Like, which one is the most electronegative?
Chlorine.
Okay, chlorine is very electronegative. So chlorine has got strong dipoles. Hydrogen, on the other hand, HBr is going to have slightly weaker dipoles. And HI would have even lesser or weaker dipoles. So the first one is going to have strong permanent dipoles. And this one has weak permanent dipoles. The molecules are not going to attract each other that strongly in the case of HI. So according to the dipoles, the first one should have a high boiling point and the last one should have a low boiling point, because there's more polarity, there's going to be more attraction. One HCl molecule is going to attract the other HCl molecule with a lot more force. One HI molecule is not going to attract the other HI molecule with enough force. But the thing is that if you look at the graph, HI has the higher boiling point. And the reason for that is that every molecule has van der Waals forces. So what happens is, the first one is a smaller molecule. So less van der Waals forces. When you go down the group, you got bigger molecules. Which means there's more van der Waals forces. So the question is, why do boiling points increase down the group, or melting points increase down the group? So what you're going to state is that even though bond polarity decreases down the group, bond polarity and the strength of permanent dipoles decreases, And why is it decreasing? Because electronegativity difference is decreasing. Or electronegativity of the halogen decreases down the group. This is a very popular question. They always ask you about this. So electronegativity of halogen decreases down the group. So that's the first part. Okay, even though the bond polarity and strength of permanent dipole decreases, but bigger molecules have more van der Waals forces. Which increase down the group, and which is why the boiling point increases. And hence your boiling point increases or melting point increases. So remember this is a very popular question, and they always ask you that what's happening, why is the boiling point of HI higher compared to HCl? And the reason is that even though it has a strong dipole, and the strength of the dipole attraction, it decreases down the group. But down the group, you have a bigger molecule. Whenever you have bigger molecule, you have more van der Waals forces. You've got more electrons. So there's going to be a lot of fluctuation happening. A lot of temporary dipole induced dipoles getting formed. And since it's a bigger molecule, the strength of the temporary and induced dipoles would be a lot higher compared to the strength of the permanent dipole because of the size of the molecule. Is this clear?
Yes, sir.
Hania, is this clear? Anna, is this clear?
Yes, sir.
So remember this, you'll always get a comment on this to explain this graph. Okay, that's a very frequently asked question. So first one, hydrogen bonds, they're always stronger compared to any other type of intermolecular force. The rest are the permanent dipoles become weaker, but bigger molecules, you have more van der Waals forces. So moving to the next part, and that is the electronegativity or oxidizing ability. If something gets reduced, I mean, this is gain of electrons. This is reduction happening. If something gains electrons, what that means is that it's acting as an oxidizing agent. So who likes to really gain electrons? The top ones are the most electronegative. So fluorine really likes to gain electrons. So electronegativity decreases down the group. So they become weaker oxidizing agents because they don't like to gain electrons when you go down the group. Iodine already has so many electrons that it's not interested in, or iodine already has 53 electrons. The same is the case with bromine. Like if you look at a bromine atom compared to a fluorine atom, a bromine atom, its nucleus already is surrounded by a lot of electrons. So it's too shielded to attract more electrons from outside. Fluorine atom, its nucleus is more exposed and it will be more strongly attracted to electrons from the other atoms. So the point is, when you go down the group, the electronegativity decreases, the tendency to gain electrons decreases, and they become weaker oxidizing agents. Anything that's getting reduced is acting as an oxidizing agent. Is this clear?
Yes.
Clear?
Yes, sir.
I said, so it's written over here. Now, the other way around. Let's talk about the negative ions. The negative ions, which are halide ions. Now, let's talk about the reverse process. I mean, over here, the elements are gaining electrons. So the negative ions are the ones that would be trying to lose electrons. So who really likes to lose electrons? Remember, smaller atoms, they attract electrons very strongly. So you've got fluorine over here, and it's going to have a very, very strong attraction for electrons. So it's not going to lose that electrons that easily. It doesn't want to lose electrons. Bigger ions, they're more shielded, they lose electrons easily. I-1 would really love to lose electrons because its nucleus would be very far away from those electrons. So it could easily lose electrons. So remember this, that when you move down the group, they become stronger reducing agents, which means that they get oxidized easily, which means that they lose electrons easily. So bigger ions, they always like to lose electrons. Smaller ions, they don't like to lose electrons. Same applies to Cl-1 to an extent. Like if you have Cl-1, it doesn't like to lose electrons. It's already, I mean, its nucleus would be very strongly attracted to those electrons. But if you look at an iodine atom, it's so iodine atom is surrounded by electrons. If there's even one extra electron anywhere, so let's say it would be very easy for it to lose that electron because it already has too many electrons. Is this clear?
Yes, sir. Yes, sir.
So yeah, both things. One of them is as elements, as atoms, when they're trying to gain electrons, the top one is the one that really likes to gain electrons and really likes to get reduced. So it's a powerful oxidizing agent. The bottom one, it already has too many electrons. It's not interested in gaining more electrons. So that means it doesn't like to gain electrons, doesn't like to get reduced. So it's a bad oxidizing agent. When it comes to the ions, F-1 really doesn't like to lose electrons. It doesn't want to lose electrons because it's a small atom, less shielded nucleus, very strongly attracted to those electrons. I-1 would really love to lose electrons. So I-1 is a pretty powerful reducing agent. Anything that loses electrons, that it gets oxidized, that's acting as a reducing agent. You clear?
Yes.
Achha, this is one thing that's very important, and that is about this reaction. I'll just do the first one. So it's the reaction of halide ions with concentrated sulfuric acid. Now, when it comes to NaCl with H2SO4, remember this. What did we just study about Cl-1? We studied Cl-1 doesn't like to lose electrons. I mean, we already know this. Like if you see NaCl, I mean, the Cl-1 doesn't like to lose electrons. It wants to remain as Cl-1. It's a bad reducing agent, which kind of indicates it's a bad reducing agent. And what that indicates is, what that indicates is, it's a bad reducing agent. So in this case, there's not going to be any redox reaction. Because for a redox reaction, you want somebody to lose electrons, you want somebody to gain electrons. Cl-1 doesn't want to do anything. Cl-1 wants to remain as Cl-1. Cl-1 is too strongly attracted to its own electrons that it's not going to give up on those electrons. Is this point clear so far? This first point, you clear?
Yes.
Okay.
Yes, sir.
अच्छा, ये तो clear हो गया कि Cl-1 or F-1, they don't like to lose electrons. I mean, अगर Br-1 hota, or if it had been I-1, they would have loved to lose electrons. So going back to this, so what is this reaction? This is a simple displacement reaction. I'm going to explain what this is. Okay, what you did was you took a beaker, you added NaCl. Now, NaCl is soluble, which means that when you mix it in water, the sodium ions and the Cl ions, they all dissociate in water, which means that they get scattered in water when you mix them up. And you have H2SO4. When you have H2SO4, it too gets mixed up in water. The H+1 ions and the SO4 -2 ions, they get completely mixed in water. So your water is now full of these ions, these H+1 and these SO4 -2 ions. So all these ions are kind of floating around in aqueous state, NaCl mixed with H2SO4. Now you'll notice that the ions are going to randomly combine with each other. So if these H+1 and these Cl-1 ions combine, what happens is they turn into HCl gas. And these ions, they leave the solution. They turn into HCl gas, which is why you see a misty white fume of HCl forming. So all these H+1 and Cl ions, they're going to mix up and they're going to form fumes of HCl gas. Is this clear?
Yes.
So what is left in your solution? Okay, the HCl, so this is the reaction that's happening. You added NaCl to H2SO4. The H from the acid and the Cl, they got together to form HCl gas and they just escaped. What is left in the solution? What is left in the solution is either Na2SO4 or Na+1 NaHSO4. That is what is left in the solution. So you clearly you get a simple displacement reaction, no redox reaction, nothing. Cl-1 does not like to lose electrons. So Cl-1 is still Cl-1 over here, it's still Cl-1 over here. The oxidation state is not changing whatsoever. Is that clear?
Yes, sir.
बस ठीक है फिर इससे आगे we'll continue tomorrow. ठीक, we'll try and finish this tomorrow. ठीक है?
Okay, Allah Hafiz.
Okay, sir. Thank you. Allah Hafiz.
Allah Hafiz.